And welcome to Lab 4 of Electrical Engineering and Computer Science 2300. So in this lab today we are going to learn about the Kirchoff laws and the superposition. So we have already conducted an experiment regarding the Kirchoff laws, right? So we all know what that is. But what is superposition? So before going to superposition, I'm just gonna, as you can see over here, the Kirchoff laws are mentioned, which is one of which is Kirchoff's current law, and that states that the algebraic sum of the currents entering any node in a circuit is equals to 0. That means in a or you can say it like if in a node the amount of current entering and the amount of current exiting, like if you do the algebraic sum of that, then that algebraic sum would be equals to 0. And when it comes to the Kirchoff's voltage law, that states that the algebraic sum of the voltages around any closed path in a circuit is equals to 0. That means if you have a loop, if you remember, then if you sum up all the voltages across all the circuit components, and if you try to find out the algebraic sum, that's gonna be equals to 0, right? So we are going to verify these laws, and at the same time we are going to learn about how you can test out this superposition concept. Okay, so superposition concept is nothing but it's a way of analyzing your circuit. And what do I mean by that? That means that we might have a circuit where there are multiple sources. So we have learned about if we have a single source and if we have the circuit elements, then how we can actually calculate the resistance, the current through the resistances, and so on. We can analyze the circuit very easily. But when it comes to multiple sources, so how we can do that? We can do that by doing so that states that in a linear circuit, the effect on the each individual component due to each source separately activated is algebraically summed when all the sources are activated. So what do I mean by that? So if you all take a look at circuit 3, so there are two voltage sources, as you can see. One is 10 volt DC and another is 9 volt DC, right? So actually if it was only 10 volt DC, then we would have exactly measured the equivalent resistance. We could like measure the current through any resistant branches, right? But when it comes to two separate sources in a single circuit, so how do we analyze that? So in order to analyze it, like what we have to do is we have to calculate what's the effect of a single source on all the components first, and then the other one. And that way, if you sum up all the results, for example, like what I'm trying to say is from figure 3, if I go to figure 1, you can see over here there are two voltage sources, right? 10 volt and 9 volt. If I go to figure 1, which is this one, you're gonna see that 9 volt is not there. That means if your 10 volt is activated, then what's going to be the effect on this circuit elements? And when I say circuit elements, I mean that all of these resistors that you see over here, right? Similarly, I am going to deactivate this portion and activate this portion, because then we have to analyze the effect of 9 volt DC over here, just like this one, and what's the effect of this source on these components. And later on we are going to sum up all those two effects, and then we are going to get the result of the total effect on all the components due to this two separate circuits, right? So now you have seen there are, so when it comes to deactivating other source and keep one activated, so in this case you can see while I deactivated the 9 volt DC for this circuit, right, that is because I am trying to see the effect of 10 volt DC on all of the circuit elements. So when I deactivate a voltage source, what I'm trying to mean is when I try to deactivate a voltage source, it has to be shorted. So you see over here 9 volt DC, it's been shorted, right? This is shorted in figure 1. So similarly, when we try to see the effect of 9 volt DC on other circuit components, then I will be deactivating the 10 volt DC. Now you might ask a question like, what happens for a current source, right? So it's totally the opposite of what we do for the voltage source. So for voltage source, we short circuit the other voltage sources, right? But when it comes to a current source, then we have to keep it an open circuit, which is if there was a current source over here, like say instead of 10 volt DC, if there was a current source over here, then this circuit at this point would have been an open circuit. Okay everyone, as you all can see, I have constructed the circuit over here. I have tried to arrange the circuit elements in a way that it resembles exactly the way our circuit our circuit manual suggests. Okay, so as you can see, all the resistor components are straightforward as it is, but you can see I have used a potentiometer, right? The potentiometer is for, if you observe the node 5 and node 3, the resistor in between the those two nodes are 1.2 kilo ohms, right? So that being the case, like I don't have any, I have 1 kilo ohms, I have 1.5 kilo ohms. So what I try to do is like set the potentiometer in a way that its resistor value is 1.2 kilo ohms. So now it's connected to the circuit, but before, like, it was totally detached from the circuit, and then I tried to adjust the resistance, and then when it was around 1.2 kilo ohms, then I just set it to the circuit. Okay, similarly you can see node 6 and node 4, the resistor between those two nodes, the value is 2.7 kilo ohms, right? So I don't have 2.7 kilo ohms, I have 2 kilo ohms, and I have 500 kilo ohms. So if I try to measure the 500 ohms, that one actually comes at 6.7 670 ohms. So I have a 670 ohms in series with 2.2 kilo ohms, and that comes around 2.78 kilo ohms. Okay, so this is the 2.2 ohm I'm talking about, and this is the 670 ohms that I'm talking about. So these two resistors would make approximately around 2.7 kilo ohms. If it's 2.8, 2.9, it doesn't matter, that's totally okay. All right, as long as you have it close. So after you construct the circuit, then you have to analyze the effect of the source. But before connection, make sure that you have everything connected as per the manual suggests. So double check everything. Okay, and what you can see over here, I have a yellow wire. So this is like, I just so see at node 6, this 2.2k node 6, like after this, this is my node 6, right? And this is my node 0. So I just didn't I just shorted this minus of the Labrador with this minus, so that it's easier for me to assemble. And after that, you're gonna see there are two steps you have to perform after assembling the circuit. One is you have to supply 10 volt via Labrador, just like figure 1 suggests. Okay, and then you have to first measure the current that's passing through. So in order to measure the current, what you have to do, you just disconnect this one, and then you just set your multimeter probe to 20 milliamps, and then you just measure the current through it, just like you did before. Like, how do you measure the current with the help of a multimeter, right? You just perform that, and after that you have to measure. If you see table 1, there are all the voltage measurements. You have to put all the voltage measurements there across every resistor, right? So when it says for example, measure the voltage across node 2, what is the voltage across node 3 and node 1, if you observe table 1? So in that case, what you have to do is, when it says V31, that means the positive probe of the multimeter, you just put it on third, and the negative probe, you put it over here, and then you measure the voltage. The plus and the minus signs over here are very important. Okay, the way you hold it, this is very important. For example, if it says 3-1, and if you hold it over here, then whatever the sign convention says, you have to just reverse that. So it's just better to follow the instruction the way the table suggests us to take the reading. Okay, so you do that for figure 1, you have to do the same for figure 2, and then you have to sum all of those value up. So what do I mean by that? I'm going to explain it in the next step. The circuit that you guys are seeing, this is the circuit for figure 3. So for figure 2 is straightforward, is very much straightforward as it was for figure 1, which is you have to deactivate the 10 volt source and activate the 9 volt source, and construct the circuit as the figure suggests, right? So after you take the reading, you construct figure 3 circuit. So here I have the figure 3 circuit. Like I said, for figure 2, instead of using 9 volt through the Labrador, I use the battery. Okay, the reason why I use the battery is because this is what I'm gonna use as my 9 volt source while constructing figure 3. So I had this one in place while taking the measurements of figure 2. Now what you are seeing is figure 3, like I said, and I have 2 volts, two voltage sources activated. Still I haven't connected this to my PC, but when I do that and supply 10 volt, then the figure 3 would be completed. And after doing that, I'm going to take the measurements of the voltage of all the nodes as suggested in the table, which is the figure 3 column. If you see, you measure all the voltages across the nodes, like mentioned in the table of and by table I mean the figure 3 column, and then you measure the current across 1.5 kilo ohm. So in order to do that, you have to make the discontinuity and then measure the current across it, right? So that's how you do it. Make the discontinuity and then measure the current with the help of multimeter. And then what you have to do is sum of the values of the nodes. For example, for voltage of the nodes 3 and 1, you have to add up the value from figure 1 and figure 2, and then after adding those up, you have to see how much are they differing from figure 3 in terms of percentage, and then complete the superposition table. Okay, so if it is a lot, let's say 15%, 20%, that means you're doing something wrong. So it's gotta be below 10%. Okay, so that tolerance is acceptable, because we are not supplying 9 volt DC. It's almost like 9 point something, right? So the percentage error is gonna be a bit more, but that's totally acceptable as long as it's below 10%. Okay, so that's for superposition. Now for Kirchoff's voltage law verification, which is table 2, right? There are 2 loops mentioned. One is 02465 310, right? That's kind of like an inverted L-shaped loop. And then another loop is there mentioned, which is 64356. Okay, so there are other loops like you see the third column of the table 2 that says your loop. That means you can take any other loop into consideration apart from this 2, and then you have to verify the Kirchoff's voltage law. Okay, so if I were you, I would take 24602. So that is the loop that's for the below one. Okay, 24602. So that being the loop, if that's your loop, then what would be how could you justify Kirchoff's voltage law? I guess you guys already know that. So you have to take the readings and then you have to calculate the percentage of error. So in this case, we know that the sum of all the voltages in a loop, that's the algebraic sum is going to be 0, right? So you have to calculate the percentage of error for this case as well, and then after you take all the readings, then you're going to be done for this lab.